Adios, Unit 1. Hello, Unit 2. We are starting to look at atoms, and then eventually we'll get into ions and isotopes. But the big idea for today, and there's actually quite a few. Sometimes we go through a chunk that's just one big idea. There's a lot that gets thrown at you here with figuring out what the atomic structure is like, and what it means to be a neutral atom, or how we can take this information and calculate what other parts would have to be there. So it's by no means like crazy difficult, but it's just something that you might have to work through a little bit with a tiny amount of practice. It's going to pay huge dividends for you on making things easier. So I'm going to assume that you've got these completed and that you'd gone through the lecture on your own and your notes are fairly completed, but I just wanted to review and kind of hit on some of the high points here. So we should be at a spot where if we talk about atoms, you just kind of think of those as being the basic building blocks of matter. And just basically means that everything that exists is going to be matter. And you should be good with defining matter from Unit 1, where we said it's going to be something with mass or stuff and volume or space. So now we're just saying, look, if it's matter, we know that it's something that's got mass and volume. It's made up of atoms. At some point, you can break it down into atoms. And those atoms might be bonded, or it might be something like when we talked about pure substances, where it's just an element, where you could literally just break it down into one part of an atom. But we're going to actually get to a spot now where we start to say, okay, well, if everything's made up of atoms, what are atoms made up of? And it turns out atoms are made up of some parts. So these are going to be referred to as subatomic parts. So are atoms made up of parts? Yes, indeed they are. And they're subatomic parts. So this prefix sub, it just means below. So when we say like, oh my, we might have a snow day or we might have a cold day, we're going to have some sub-zero temperatures. You know that means that the temperatures will be below zero. Or if you think of like a submarine, marine, ocean, sub, below. Guess what submarines do? They go below the water. So subatomic particles are really just saying, okay, well, if we look below the atom, what's it made up of? And we keep it pretty simple. If you take higher levels of chemistry or physics, you'll see that it gets a little bit more complex than this. But we're just going to keep it simple here. And as far as the particles that we're going to go through for the subatomics, they're the big three, I would call them. And it's going to be protons and neutrons and electrons. So these are the three that we have to keep straight. And protons, you hear pro, usually think of it as being like a positive or a good thing. Protons have a positive charge. So I've had some kids that will think, okay, well, neutrons, they must be negative because it starts with an N. No. Think about neutrons. You're almost saying neutral. So these are going to be a neutral charge, or there is no charge on them. So if these guys are positive and these guys are neutral, electrons are going to be our negative charges. So I'm just going to put a negative there. If you wrote in positive, neutral, negative, fantastic. But this is definitely something that we've got to get real comfortable with, is knowing that protons are positive, neutrons are neutral, and electrons are negative. The other thing that we need to know is how much mass they have. This is kind of keeping it, again, pretty simplistic, but it'll be okay to get the big ideas across in Unit 2. We're going to say a proton has a mass of 1 AMU. So this unit AMU, we haven't used it yet in Chem A, but this stands for atomic mass unit. And it's basically something that is going to be able to measure something that's as small as a tiny, tiny subatomic particle. So, we'll get into a little bit more detail down the road about just how small atoms are. But at this point, it's almost like kind of mind-blowing to think about how tiny they are. So when we were looking at like mass back in Unit 1, we use grams. Well, grams, if we're using that to measure protons, we'd have some crazy small number where it's like 0.00000000000, so on, so on, so on, 1. And we don't want to work with that. So what chemists and physicists have done is they said, look, let's just kind of scale this back to where we've got easier numbers to work with when we're trying to measure these guys. So this is a new unit called the AMU. And neutrons have a mass of 1 AMU. Electrons, this isn't really 100% accurate, but again, I'm going to kind of try to simplify things a bit to get us through this second unit. We're just going to say that electrons have a negligible or a 0 AMU mass. I mean, they exist. Do they have a mass? Yeah, but it's literally so small, even on this AMU scale. I'm going to round down to 0. I want you to know that that's not really accurate, but we're just going to kind of round down to 0 so that we can think, okay, well, protons and neutrons, they have the mass in the atom, and the electrons do not. So rather than writing out protons and neutrons and electrons, you can use these little symbols where it's P for protons, and then up here in superscript is a plus because it's positive. Neutrons, N. Neutrons are neutral, 0. And electrons, they're the negatives. So we have lowercase e and then up in superscript. So a lot of times if you see these symbols, it's just a shortened way of writing out protons, neutrons, electrons, and it also gives us a reminder of their charge. Some of you are probably in driver's ed. And you know that if you're looking at a vehicle and you've got R and D on your gear selector, if I put the vehicle in drive, whoop, it goes forward, kind of like in a positive direction. And if I put the vehicle in reverse, whoop, it goes backwards, kind of in a negative direction. And if I leave my vehicle in neutral, it's just in between, or it's in the middle. So that's what neutral is. It's kind of in between, or it's in the middle, or a lot of times we'll just say it has no charge. So down the road, keeping this straight with which ones have charges and what their masses are is going to be pretty important. So you need to be aware that when we deal with protons, yeah, it's got mass and a positive charge. And neutrons, yeah, it's got mass, but it does not have a charge. When we look at electrons, there's no mass, but there is a charge. So this guy having mass but no charge, and this guy, by which I mean electrons, having no mass but having a charge, those are things that you're going to want to get straight in your head. I promise you it'll make things easier down the road. So there was this genius by the name of Niels Bohr, and he came up with a model of the atom that we still kind of use today to get ideas across. It definitely gets more involved, but basically a Bohr model. It's going to have a nucleus that's got protons and neutrons. That's where those guys live. And then in these energy levels that we'll talk more about later, that's where the electrons are at. So these can fill up and then electrons can spill out. But really what I need you to think about for today is you've got to think, okay, well, in the nucleus, there's a protons and neutrons. That's where those guys live. And on the outskirts, kind of orbiting around, almost looks like a little solar system, right? Like there's a sun and there's where the planet's path would be or orbit would be. Electrons are orbiting outside of where this nucleus is. So the atomic number. This particular periodic table doesn't have a key or a legend on it. I can get you some, or you can use whatever you'd like off of the internet. And it's going to have keys or legends on it. But I'm kind of familiar with the periodic table. And I can tell you that on this guy, in the top left corner, that is going to be the atomic number. And if you look here, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so on and so forth, kind of back and forth. The periodic table, it's got this kind of weird sort of U shape to it, and there's a lot of things going on here that we'll talk about in a later unit. But right now, I just want you to know, okay, that atomic number, it's that top guy. And the atomic number is the number of protons. So guess what determines an element's identity? Protons. And this is huge. You've got to keep it straight in your head as we make our way throughout all of chemistry that you can never change the number of protons. So when we start looking at charges or masses, if you're like, oh, okay, well, boron, it's got 5 protons. Well, if I wanted it to be positive, then I'll just add some more protons. No, no, no. If I add a proton to boron, it's going to become carbon. And you can't do that. So if I can't ever change protons, that really only leaves me with 2 things I ever could change: neutrons and electrons. And down the road here, we're going to see, yeah, when you change the electrons, you get what's referred to as an ion. And when you change the neutrons, you get what's referred to as an isotope. But right now, I just want you to get straight in your head. Atomic number, it gives the element its identity. Why? Well, because that's the number of protons in the nucleus. That is why calcium is calcium. It's got 20 protons in its nucleus. What about magnesium, Cash? Well, it's magnesium because there's 12 protons in its nucleus. So that's the way that we kind of say that elements are identified. It's by the number of protons or its atomic number. So as you were going through these, if you didn't have a periodic table, goodness gracious, I certainly would never expect you to have all this memorized. But if I look at like 5, it's boron. Or if I look at like 88, it's radium. Or if I look at like 16, it's sulfur. So these elements are always going to be boron or radium or sulfur, because if this is atomic number 5, even if I were to say, hey, there's an element with atomic number 5, how many protons does it have? 5. Atomic number 88, well, that's got 88 protons. Atomic number 16, that's got 16 protons. So, again, you could look there and say, oh, okay, well, yes, it's atomic number 16. That clearly means it's got 16 protons. So that's got to be sulfur, or that has to be radium, or that has to be boron. But I do want you to, like, if you've got a periodic table that you know you're going to be using, what I would do, I would have something on here so I'd never forget. Atomic number equals protons. So then I'm always thinking, okay, well, the atomic number, that is the number of protons. And, if I've got that up front there, I have that to refer to, and that's handy. So I want to know that I can't change that. So I might even put in parentheses here, can't change. So then when I look at this, I'm like, okay, down the road, not so much for today, this is the number that I can't change. But I can monkey with the neutrons and the electrons, and we'll get into that a bit later as well. So there is a mass number, and this little guy does not have a key, but the atomic mass, I'm going to jot this down here because I want this for every time I grab this one. My atomic mass equals my protons plus my neutrons. So what's your atomic mass? Well, okay, atomic mass, that's going to be my mass number here, or my protons plus my neutrons. And if you remember, we said protons and neutrons, they live in the nucleus. Sometimes if we're talking about both these guys, we can use the term nucleons. So if I said it's the nucleon, it's just a one-word term, so you don't have to say protons and neutrons. So like I said, this is a lot of information to throw at you, but I promise you, as you just kind of work through it all, it starts to kind of stick, and everything will work out much, much easier if you can commit this to memory, or organize your periodic table where you've got enough reminders to where we're going through a quiz or a test, you can refer back to that and you understand what it is you were trying to get at. So here's kind of like some simple algebra. Neutrons. How the heck can we calculate neutrons? Well, let me tell you. If I take the atomic mass and I subtract the protons, I'm left with neutrons. Or, think about it kind of like this. Remember when I said atomic mass is your protons and your neutrons? Well, if I'm looking at this, by this I mean the periodic table, I can always tell how many protons are in an atom, right? How many does aluminum have? 13. That is what the atomic number is. That's how many protons are there. Okay, well, how many neutrons are there? This doesn't come right out and tell me. But if I go back and I think, well, the mass is made up of protons and neutrons, and remember we said electrons doesn't even have mass. If I wanted to figure out the number of neutrons, I could take the atomic mass, subtract out the protons, and then what I'm left with is the neutrons. You might be saying, well, what about electrons? Well, remember again, we said electrons, they don't have a mass. So they don't really factor into this. Are electrons important? Oh, goodness gracious, yes. They're huge with bonding and charge and all that stuff, but that's not today. Today, we're just trying to figure out how many neutrons would be present in aluminum. So you can't have a fraction of a subatomic particle. And down the road, I'm going to explain to you why this has 26.98. But if you were to take 26.98 and subtract 13, you're going to get some change. You can't have a fraction of a neutron or a tenth of a proton or 0.375 of an electron. You either have one of these subatomic particles or you don't. So what do? You round. So like for this example here, if I had aluminum, 26.98, think about it. If you had $26.98, you're pretty darn close to 27 bucks. I would round that up to 27. So if there's 27 for my mass and 13 of it's coming from protons, then that other 14 has to come from neutrons. So if I needed to figure out the neutrons, I might have to round the mass because I know I can't have a fraction of a proton or a neutron or an electron, pull out the protons, and what I'm left with is the neutrons. So if I had to calculate the number of neutrons in carbon, let's take a peek. $12.01. No, it's really 12.01 AMU. I'd round that down to 12. 6 of that comes from protons. So if my mass is 12 and I subtract out 6, I'm left with 6. So that means that there would be 6 neutrons in carbon. So if I'm kind of going through this guy here to wrap this up, here's a little bit of review for us, right? Protons, positive. Electrons, negative. We're going to talk about neutral atoms in the near future. And if I say something's neutral or it's balanced, remember just like with our car, that means it's in the middle. Now I want you to kind of think almost like a teeter-totter or like a little kid's seesaw, right? So, boop. And you know how seesaws work, right? You got a kid on this side and a kid on this side. And I know that if this kid's too heavy, whoop, or if this kid's too heavy, whoop. But if they weigh the exact same, or if they adjust their distance from the fulcrum, which we're not going to get into today, if I got the same weight here and the same weight here, it's going to stay nice and straight or balanced or neutral. Well, we're not dealing with weight here, we're dealing with charge. So if my protons equal my electrons, then we're going to be balanced or we're going to be neutral. So what's it mean to be balanced? That's when your protons equals your electrons. So now here we're talking about charge. We kind of made a jump, right, to where we were looking at the mass before to calculate out the neutrons and stuff. Now we're kind of looking at charges. So if we say something's neutral or it's balanced, that's in reference to its charge. And if your positive guys equal your negative guys, then that's going to be balanced. So what is a neutral or balanced atom? Again, that's going to be when your protons equal your electrons. So if I'm looking at the periodic table, I don't know, chromium, it's got 24 for an atomic number. What's that mean? All right, well, the atomic number is the number of protons. So if I had 24 of these guys, 24 positive guys, how many would it take to balance that out? 24. So if I had a neutral atom or a balanced atom of chromium, 24 positives, I'd need 24 negatives or 24 electrons. Cash, do another one. Okay, let's take a look at lithium. If lithium's got 3 for an atomic number, 3 positives, well, how many positives is that? 3. Okay, what would balance out 3 positives? 3 negatives. So it'd be 3 electrons here if it's balanced or neutral. So So down the road, we'll see they're not always balanced. They're not always neutral, but today's not that day. We're just kind of getting our feet wet with all this. So sketch an example of a neutral atom. Okay, let's do carbon. I like carbon. So if I'm going to jump down here, just have a little bit more space. I'm going to say, well, here's carbon. And it's got 6 protons. So that's supposed to be P with just a positive, up in my subscript. And if I look at this guy, remember, I think I did this one already with you, right? If I'm going to say the mass is 12, and 6 of it comes from protons, and I wanted to draw on the neutrons too, well, if the mass was 12, so we got to round it, we can't have a fraction of a proton or a neutron or an electron. 6 of it was protons. I'm left with 6 neutrons. Let's throw those guys in there, right? And it's just kind of coincidence. These aren't always the same. It's just with carbon in this example, it works out to where I've also got 6 neutrons. And I'm going to kind of put those guys here. That's going to be my nucleus. Or you could refer to these guys together as like the nucleons. The nucleons live in the nucleus. They're your protons and your neutrons. And this is not a real good, accurate bore, but I know the electrons live around in these orbits or in these energy levels. I haven't talked to you about how many they can hold or anything yet, but if I've got 6 positives, I got to have 6 negatives. Turns out this first shell can only hold 2. I would not expect you to know that yet, but there's 2. So then I got to have 6 total, right? I'm just going to kind of sketch mine in to look like this. So if your sketch didn't look like this, that's fine. If you were just kind of saying, okay, well, look, if I got to do a neutral atom, and, again, say it was like carbon, and you said, well, there's 6 protons in the nucleus, and that means I've got, say you had like 1, 2, 3, 4, 5, 6. For now, I'm okay with that. Maybe you dazzle me by showing protons are positive and electrons are negative. But, if I go back to like my little teeter-totter example here, if I'm saying, all right, on my positive side and my negative side, if I've got 6 protons, gosh, why 6? Well, because I just use carbon as the example. Well, how many are going to balance out 6? 6. That's the way that works. So this would be a neutral or a balanced atom. A lot of information. I get it. I promise we'll go through it slow and steady and often. But as always, you've got questions, concerns, please see me. And, until we meet again, enjoy the day.